Okay, so the next thing to talk about is about Kummer classes of functions. So Kummer classes of functions. So let's take K to be a field. X is going to be a scheme over K. And we'll think of it as affine so that it has functions on it. And what we're going to do is we're going to associate, so the construction is as follows. So we're going to associate to each function here so there's this map, kappa, the Kummer map, into H1 of, let's say, X of Z hat 1 of X, and I'll say what this is. Taking this guy here to kappa, and it'll be associated to, so this is the Kummer class, Kummer map associated to X and F. So this is this guy here is the Kummer class. Okay, and so this is what will be the group theoretic. I don't know. This will help us with group theoretic evaluations of functions. So we're going to find a way in order to from this particular cohomology class to know what f evaluated at points of the scheme are. So this is what we're going after. Okay, so let's start. So recall that we have this baby Kummer sequence. Kummer sequence. Okay, and as all Kummer theory, it always starts with the following sequence. So this is a sequence of group schemes. I've kind of omitted what the base is here. So this is a sequence of group schemes, but we're going to, so this could be, say, over K, okay? But we want to view this, the sequence as group schemes as, let's say, atoll sheaves of groups. Let's say X atoll, so we're looking at atoll coverings. Let's say sequence, we want the sequences or sequence in this guy here. So what we do is we just base change the X. So to do this, we base change the X to X, okay? And this gives us 1. So these things were over K, so it makes sense to take the fiber product over K with X. And we have a sequence like so. And a lot of the times I'll omit the subscripts X. So this is multiplication by N, in the group law here. Okay, and so this is an exact sequence of sheaves on this. Okay, so how do we view this? So let me just say a little bit about how this is viewed. So we let's note that maybe this is kind of like a little aside here, that if X prime to X is an atoll cover, then we have this natural action of pi 1 of X, so this is the atoll fundamental group, acting on X prime by deck transformations. And hence, so this gives us, I guess it goes as this, which gives us that an exact sequence here of 1 from mu n x prime to g m x prime, g m x prime like so. So this is an exact sequence of pi1 modules. So what we could do is we could have done this, we take like the universal cover points and then looked at the sequence as pi1 modules, or we can look at it as group schemes. And these two ideas are kind of interchangeable. And in fact, for finite groups, or for finite group schemes and limits of finite group schemes, the group cohomology will coincide. The group cohomology with the étale fundamental group will coincide with the étale cohomology. All right. So anyway, this was a little aside thing about where these group actions are coming from. Anyway, we can consider this sequence, and then we can consider the associated long exact sequence. Now let me just say that from now on I'm going to omit the subscripts and so that we can understand, we'll understand these as sheaves on X without saying where the X is. Okay, so we consider the associated long exact sequence and in the long exact sequence, we have this connecting map where we have h0 of x at gm goes to h1 of x mu n. Okay, again, these are the group schemes on X, and I'm going to call this connecting map kappa subscript X at the nth power here. I want you guys to note that this guy here is OX cross. So this is already kind of the baby Kummer map here that we're after. Okay, and so so now we have this sequence here. Because that this dude is representable in, say, the derived category. Actually, I'm not. Let me just say that there's a fact here. There's a fact, and it says that this limit, this inverse limit of this cohomology, mu n, okay, and I guess it's on X. I'll write it this time again. So this is equal to h1 of x of the inverse limit here, mu n of x, and this is equal to h1 of x, c hat 1 of x. I guess we could define it this way. Okay, so the definition of this limit, so I guess this is a pro-group scheme anyway, and so we could define the cohomology of this to be this. All right. Okay, so we have this, and we get a map. So, okay, so now we have this thing, and this tells us, so we get a map, here, kappa hat of x, from h0 of xgm to this guy, c hat 1, by taking limits. By taking limits. So let me just write this down on the next page. This dude here, this Kummer map, is the inverse limit of these guys. Great. So what have we done? So the summary of this, okay, is that again, for each dude in here, F, we can map it to, and I'm going to use this notation, kappa x of F, which is just, we're going to just call kappa x comma F, okay? Or maybe just kappa of F a lot of the time, okay? So a bunch of different notations, and it's going to live in the cohomology here of z hat 1. Okay, and then I also made the remark that, by the way, that this guy here so this is the same thing as the inverse limit, or sorry, as the group cohomology. And I'm omitting base points here, but we could choose base points to make this for each base point. Okay, so morphism should really be morphisms of pointed things. All right. Okay, so what actually is happening is that there's some functoriality going on. So let me try and introduce this concept with respect to morphisms. So what actually is happening is that we have a functor kappa from this dude GM. So I guess it's a natural transformation of functors. Z hat 1. Okay, so this guy, this is a natural transformation. Let's see, is a natural transformation, like so, for functors from schemes over K to abelian groups. Okay, both of these are schemes over K to abelian groups. Okay, so in particular, if we take some map, okay, we get the following diagram. The following diagram is like so. So I'm going to write out the one that we had before. This is for GM. This is the kappa hat of X. Hat 1. Okay, and so now this is the group scheme on X. This is kappa hat of Y. Okay, so we have a morphism from Y to X, and actually these arrows should go the other way. Okay, and this map here is, well, what happens when you take H0 phi of GM. We'll just call this the pullback. And then this thing is H1 phi of Z hat 1. And we'll also just call this a pullback. Okay, so we have this compatibility whenever we have a morphism between these Kummer maps, and taking Kummer classes gives us this sort of compatibility. So when you pull back a function, so here is this. So this, when you have a function on X, you pull it back to Y, and you take its Kummer class. This is the same thing as taking its Kummer class and pulling back the function. Okay? This functoriality property is important because it allows us to evaluate functions. Because it will show us evaluation of functions at points factors through cohomology classes. Okay, and then the idea will be to reconstruct the cohomology classes together with the evaluation points. Okay, so let me move on to this next part. So this is group theoretic evaluation. Or maybe I should say cohomological evaluation. So this is maybe the cohomological part. And then the group theoretic part will be a little bit more. We'll have to say a little bit more about this. Okay, so as in the previous example, or the previous, let's say, subsection, that we can take y to be spec k and consider rational points. Let's say spec k here, where a is like this. So, i.e., elements, points. Okay, and so what does this give us? So this gives the following. So we had the h0 of xgm, and then we have, so let's call this, I don't know, this is A, or we could call it phi of A, so we could call this A star of F, or sorry, A star of, we just call this A star, I suppose, right? So let's just call this A star, to be consistent. So this is A star. Here, this was H0, and then we had spec of K. I'm just going to write K, GM. Okay, so this is just K star. Then here, we had this Kummer map, kappa hat of K. And then we had the Kummer map here for X, kappa hat of X. So this went to H1 of X, Z hat 1. This goes to H hat of K, Z hat 1, like so. Okay, so this is also A star. Okay, by what we said in our notation. Okay, and this thing here, this port here, so this is the kind of the interesting part. This guy here takes a function f and it maps it to f of a in here. So this guy here is the usual evaluation of functions. Another way to think of it is that if you have a function and you restrict it to a point, that's really like, scheme theoretically, like modding out by a point, modding out by the ideal of the point, and so this is really an evaluation map. And so the commutativity of this diagram says that if you take the Kummer class and then use this pullback on group cohomology, then this should be like evaluation at a point. All right, well, let me just write what that this all says. Writing out what this says, it says that kappa hat of K of f of A. Okay, so that's this part here. That's the same thing if we were going to go around the diagram the other way. So this is A star of kappa hat x f. Okay, as elements of H1 K Z hat 1. Okay, so this is kind of an interesting relationship. So this is again the relationship between evaluation of points in Kummer classes. Okay, now I want you to recall something that we did earlier, and so let's recall. that we had these isomorphisms here, delta n, which we called kappa n of k. Okay, so this is from k cross to the n to, this is an isomorphism between h1 of k mu n. Okay, so okay, and this is the co-kernel. So this came from the exact sequence, right? And this induced this map here, delta hat. So this limit, this inverse limit of these guys, which is so this guy here. Let me get rid of that. Delta hat. And delta hat was from k cross hat into h1 of k, z hat 1. Okay, so we have this isomorphism here. All right, so putting these two things together, so this is from a previous video. We had this isomorphism here that we described, and we have this thing here that we described. Okay, so in particular, so we have, putting these together, gives the Kummer theoretic evaluation. It says that f of a is really delta hat inverse, and then if you take a star of kappa, the one associated to x at f, all right, we take this thing, and this is what it is, as elements of k cross hat. Okay? We have this special formula. So in particular, we have f of a is in this dude, which is naturally included into the completion via its inclusion. All right. So again, this is kind of cool, right? So we have this guy. We have this procedure where we take a function and we evaluate it, but then we saw previously that this thing here is really k cross hat, like so. And this is delta hat inverse. So what we can do is we take the Kummer class. So we have f. So this f maps to its Kummer class, kappa of f. And then when we pull back the Kummer class to a class here, so a star of kappa of f, okay, and then look at it under this natural isomorphism that we have, well, that's the same thing as if we were just going to evaluate the function. Yeah, so that's kind of cool. Lastly, I just want to say that there's another important component to Kummer classes, and the idea is the following. If we have a Kummer class of a function, let's say it's an h1 of pi of x with coefficients. Okay, we saw that the function here, gk to, so this, we had this map, and then if we had a section, that this section induces a pullback, right? It induces, so this is a section associated to a point of the curve, and this induces a map. This is isomorphic to this profinite completion. And this guy here, okay, so we want this all to work. If we have a section, this is all nice and good. But one of the issues is that this guy here is only well defined up to conjugacy. All right. Okay. So maybe it feels like I lied to you. So eventually, what we want. So the eventual goal. Okay. So we need to deal with this. So one thing is we need to deal with this. And the second thing is the eventual goal. We want to take the image to just use the image of S. Okay, so if this is a genuine morphism, so equals, and then so this is if a morphism of groups say not outer. Okay, so, or in particular, we can take one of these sections. This will be the decomposition group of x tilde over x, which is a subset of pi of x, to evaluate. So, okay, so what am I saying? So, okay, so this is S of x, so we have this cuspidal section. Eventually, we just want to take the image here. This is going to be a decomposition group of a cusp, which we can reconstruct. And then we just want to be able to use the decomposition group to evaluate the function, to evaluate the kappa of f. Okay, but maybe that's not the best English, but whatever. Okay, so again, so what did I not say? So the idea is that given this, if we have this functorial construction, right, then we have this map here. Okay, if we have a genuine section, then we have this pullback map, and this would allow us to commute. This would allow us to evaluate the function. Okay, the problem is that this function here is only well defined up to conjugation. Okay, so that's in another video. And yeah, and so we want to apply this method. Okay, so we need to deal with this conjugacy and determining, and eventually we'll want to just use the decomposition group of the function, not the section itself. Okay, and these things, and the point is that these guys here, these decomposition groups, can be reconstructed, can be given an Anabelian interpretation. All right, so this is what I wanted to say.